Okay, let's get started. Any questions so far? Any questions? Okay, so what we have to do is check player one's expected payoff if he uses another correlated strategy, another complete plan of action. We keep the strategy of player two fixed, that is the strategy, the correlated strategy of the other agents. Well, there's one other agent fixed, so let me write that here. So if the outcome is R, player two will go to the opera. If the outcome is C of the random experiment, player two will go to the soccer match. So that's fixed. What can player one do? Well, what are the possibilities? Oh. So go to the opera no matter what. That's one possibility. SS. Go to the soccer match no matter what happens, right? And SO. Go to the soccer match if it's rainy. Go to the opera when there's no rain, when the sky is clear. So let me write the action of player two here also. So under this case, what is the expected payoffs? So it's again, with 1/2 probability, it's going to be rainy. And if player one uses this correlated strategy and player two uses this correlated strategy, then player one's expected payoff is going to be 1/2. If they both go to opera, player one was the one who preferred the soccer more. So that's 1. If player one goes to the opera and player two goes to the soccer match, his binary utility was 0. So that's 1/2. Under this case, I'm going to go fast this time. 1/2 times 0 plus 1/2 times 2, right? So that's equal to 1. And then in this case, it's 1/2 times 0 plus 1/2 times 0. In both events, they end up at different places. So player one's payoff is 0. Okay? So if he plays according to sigma 1 prime, his expected payoff is 3/2. If he plays some other correlated strategy, his expected payoff is either 1/2 or 1 or 0. So no matter what he does, he can't get an expected payoff greater than 3/2. Okay? Well, we do the same exercise for player two, and you will see that that's also the case. Okay? So this 4-tuple, this random device, together with this correlated strategy profile, is a correlated solution of the battle of sexes game. Okay? So far, so good? So far, so good? And player one's expected payoff from that is 3/2. And so is the expected payoff of player two. Okay? Okay? Which is, if they played the mixed strategy, the Nash equilibrium of the mixed extension game, well, I shouldn't say the Nash equilibrium, there was 3 of them. The Nash equilibrium was completely mixed. What was the expected payoff of the players? So that we're talking about of 2/3, 1/3. Player one uses this mixed strategy. Player two uses this mixed strategy. So the outcome is going to be 2/3 times 1/3. They choose independent random devices. So with probability 2/3, player one will go to the soccer match. Stochastically independently, player two will choose to go to the soccer match with probability 1/3, okay, which is equal to 2. And then we continue 2/3 times 2/3 times 0. So player 1 goes to the soccer match. Player 2 goes to opera. They're at different places. 1/3 times, what did I, the first number. So 1/3, he goes to opera. 2/3, player 2 goes to opera again. So that's a payoff of 1 plus 1/3 times 1/3 times 0. What does that give us? Sorry? 2/3, okay? I'm bad with calculations, so which is less than 3/2. Okay? Which is, again, less than 2, the maximum payoff that player 1 can get at the Nash equilibrium, and greater than 1, which is the other payoff that he can get by playing the other pure strategy Nash equilibrium. Okay? So far, so good? So far, so good? Okay. So with the correlated equilibrium, they got a higher expected payoff. Why? Okay. Because they were able to coordinate their action, and so that they were able to avoid such situations. They were able to avoid ending up at separate places. Okay? So far, so good? Any questions? Any questions? Sigma 1r
equals to sigma 2r equals to s.
Sigma 1r equals to sigma 2r equal to s. Okay, that's also, you have to check it, but yes, that is the case. Actually, would you like to try this one too? So, well, this is not complete yet, right? To make this into a correlated solution, we also have to specify correlated strategies. So can you, let's choose a correlated strategy for player 1. So we have to tell what he does. Actually, let me just use this. Okay, you want to try this too? Yeah, let's try. Exercise is good. So I'll try to write better this time because it's going to be a larger table. Outcome, HH, HT, TH, TT. Sigma 1 omega, sigma 2 omega. So, give me a correlated strategy for player 1. So if he learns that the first toss resulted with a head, he will go to the opera. If he hears that the first toss resulted with the tail, he'll go to the soccer match. Okay? What about player 2? The same. Okay. Exactly. Okay, exactly. As soon as I wrote this, your friend noticed that this cannot be a correlated strategy. Why? Look at the information partition of player 2. Player 2 cannot tell the difference between this outcome and this outcome. Okay, in both of them, he's told that the second toss resulted with a head. so he cannot choose different actions. So this is not a correlated strategy for player 2. So what we have to do, so you want this opera, soccer, or opera, soccer. Okay, so far so good? Any questions? Okay, so this is a correlated strategy for player 1. This is a correlated strategy for player 2. Again, you have to be careful about the assignments. Okay, so far so good? So expected payoff of player 1. Of agent 1. So it's going to be, well, we said the friend, the outside there, tosses a fair coin twice. So it's 1/4. With 1/4, the outcome is going to be this. And as a result, the actions taken will be this. And as a result, player 1's payoff is going to be at 0, he was the soccer lover, so it's going to be 1/4 times 1, plus with 1/4 probability, the outcome is going to be HT. And they will take this action. And the payoff of player 1 in this case will be 0. They're at different places. They don't like that. Plus, with 1/4 probability, the outcome of the random experiment is going to be HT. They're going to take these actions, and the payoff of player 1 is going to be 0. And with 1/4 probability, the outcome is going to be TT. They're going to take this action, and the payoff of player 2 is going to be, player 1 is going to be 2. So what does that add up to? 3/4. Okay? So far, so good? So can player 1 do any better by choosing a different correlated strategy? Okay, so what? Sigma 1 prime omega, sigma 2 omega. I'll write that because I get confused. So there's no change in player 2. O, S, O, S. Okay. So always? Always S. Okay. So then what is the, so actually let me write the payoffs here. So it's going to be 0 from this outcome, 2 from this outcome, 0 from this, and 2 from that. So his expected payoff is going to be 1/4 times 0 plus 1/4 times 2 plus 1/4 times 0 plus 1/4 times 2, which will give us 4/4 or 1, which is bigger than 3/4. Which means that this strategy profile, together with this random device, this probability space, does not constitute a correlated strategy. Correlated equilibrium, I'm sorry. Does not constitute a correlated equilibrium or a correlated solution of this game. Okay? Could you please sign and pass around? Okay, any questions? Any questions? Well, question? So player 1? Uh-huh. Player 1 always goes to the soccer match no matter what. Yep. So you're thinking about deviation from the deviation. So we were considering this. We asked if player 1 knew that player 2 or guessed or they shook hands. Okay, in the morning, they agree on that. They shook hands, but they can't make any binding contracts. Otherwise, the game changes. We'll be analyzing a different game. Okay. Okay. Given that player 1 believes that player 2 is going to play according to this correlated strategy, will he be better off by deviating to some other strategy? And the answer is yes. So are you asking, well, is this a reasonable deviation? Well, if player, you see, anything that player 1 can think, player 2 can think also. So maybe player 2 will also deviate. Okay, but that's a different solution concept. And if time allows, not today, but toward the end of the semester, maybe we'll do that too. Okay, but here, the basic idea, so if there is a deviation from the deviation, then maybe my deviation is not a reasonable thing to do. Okay, so maybe if, when I deviate, the other player will also deviate, and then I'll end up with something less than 3 over 4. Okay, but that's a different solution concept. Okay, for now we don't consider that. Okay, but that's an interesting point. And unfortunately, some game theorists have already asked about it, so otherwise you could have invented a new solution concept now. Okay, any questions? Yep. Well, wait a minute. So first of all, you have to be careful. A pure strategy, Nash equilibrium, is a strategy profile, is a list of actions that the player is going to take. A correlated equilibrium, a correlated solution concept, is a complicated animal. It's a random device, a probability space, together with correlated strategies. So how can we compare these two? How can we say that any pure strategy is also a correlated strategy? Which we might be able to do, which actually we'll get into.
So you're saying that the most part is sigma.
Sorry?
For every
So what is omega? First, you have to tell what omega is.
omega is the set of natural, like all the possible states of natural event, for example.
What is a natural event? Is tossing a coin a natural event? Is the weather a natural event? Is rolling a die a natural event? So you have to specify what omega is. Tossing how many times?
Two times. For example, we have,
Here, okay.
by saying that sigma I for every state of the world is S, for example, for both players, then it's also a correlated equilibrium.
Okay, so your friend claims that. Okay, so more generally, take any random experiment, take any probability space, okay? For each player, take sigma I omega to be equal to SI star, where SI star is, well, actually, let's start this way. Actually, let me erase this part. Okay. By the way, I'm going to erase this, but try to find a correlated strategy which, together with this probability space, together with this random device, will be a correlated solution of the battle of sexes game. Okay? So we tried one, it didn't work. Okay? So maybe you should try this or try something else. Okay? But give it a try. If we had time, I would like to do it, but let me first write down what your friend suggested. Okay, so if I understood correctly, given any, so, well, let's start with this. Let S star be a Nash solution of the original game. Okay, so given any probability space, random device, omega, pi, okay, define for any I in n, define sigma I from omega to Si as sigma I, well, sigma I of omega is equal to Si star for any omega in capital Omega. This is a correlated strategy. It satisfies the conditions that we have here. Your friend claims that this random device, this probability space, together with correlated strategy profile defined in this manner, is a correlated solution of the game gamma. Okay? What do you think? What do you think? I'm glad that this time I didn't raise this. So with that, what do we have here? This is going to be Si star. This is going to be S minus I star, right? If they play according to the strategy. This is going to be S minus I star. And this is going to be, well, some strategy of player I, okay? Depending on what sigma I prime is. If S star is a Nash solution, what do we know about the relation between this number and this number? This number is greater or equal to this number. Then the weighted average of these numbers is going to be greater than or equal to. So the proof is very simple. Your friend's observation is correct. Do you all see that? Okay. So every pure strategy Nash solution can be converted into a correlated solution of the game gamma. Okay? So far, so good? So far, so good? Any questions? Yes, sir. Okay, very good. That was, I was hoping that somebody would. That would be the next question to ask, right? What about mixed strategies? So rather than starting with S star, take mu I star, which is a Nash solution of the mixed extension of gamma. Can we convert that into, can we convert again, in quotations, that into a correlated solution of the game gamma? What do you think? Everybody agree? The answer is yes, we can. Okay. Actually, so because of that, the other one comes for free. Okay, the pure strategy. If we know that any Nash equilibrium of the mixed extension game, if any Nash solution of the mixed extension game can be, again in quotations, converted into a correlated solution of the game gamma, then any pure strategy can be converted into a correlated solution of the game gamma. Because we already know that any pure strategy Nash solution of the game gamma is also a Nash solution of the mixed extension. Okay? Well, I will not write the proof of that yet, but what I'll do is, again, you see, this is a complicated animal. So when you're finding a correlated equilibrium, you have to specify, a random device. You have to specify the set of possible outcomes. You have to specify the probabilities of those outcomes being realized. You have to specify what the agents know about the result of the outcomes, okay? Which is a lot of work. And then you have to specify correlated strategies. But you see, what's happening here is, let me erase this part. So we're given an outcome set, and then agents, an outcome is realized. Agents choose correlated strategies, sigma 1, sigma 2, sigma n. And these, as a result, an element in S1 is realized, an element in S2, an element in Sn is realized. That is, an element in S is realized. Okay? Well, these are fixed. There's nothing random about it. But a probability, once you fix these, a probability distribution over this induces a probability distribution over strategy profiles. Okay? So a natural question could be, well, can we just get rid of this step and start with the probability distribution over S to begin with? That is, take the set of outcomes as strategy profiles itself. Okay? Because after all, what matters is, you see, when you're calculating these things, you're calculating the Bernoulli payoffs over strategy profiles. Okay? And then when you calculate these, sum up over all omega, which yields the same strategy profile, okay, you're actually summing up over strategy profiles, okay, Bernoulli payoffs from strategy profiles, times the probability that that profile will be played. Okay? So, and that simplifies things quite a bit. Okay? You get rid of the set of possible outcomes. So, are you going to use rain or sun? Are you going to toss 2 coins, 1 coin, roll a dice, use an urn which contains white, black, blue marbles? Okay. We get rid of all of those. We just talk about strategy profiles. Okay. So the interpretation that we will take now is, which today we might not have enough time, but is going to be, in a way, equivalent to what we have here. So what we will do is, the players will agree on a probability distribution over S. Okay? And the interpretation will be, if a strategy profile S is chosen, for example, a profile SO is chosen, we will interpret that as player 1 is recommended to play S, player 2 is recommended to play O. So rather than your friend calling and saying the first toss resulted with a head, and then calling the second player, the second agent, and saying the second toss resulted with a tail, the friend calls player 1 and says, you should go to the soccer match. And then calls the second agent and says, you should go to the opera. Okay? But he gives that information according to the probability distribution that you have agreed on. Okay? So once player 1 gets this recommendation, he can follow it, or he can deviate and play something else. Okay? So let me try to formalize that a little bit more. So what we have is, let me this time use mu hat. It's going to be a probability distribution over S. So that will denote with triangle S. That's probability measures on the set of strategy profiles. Okay. So strategy profile S will be selected with this probability. And the interpretation is, Okay, once this is selected, the interpretation is player I is recommended to play SI, the ith component of this, and the other agents are recommended to play according to their components in this profile. Okay? So if player I follows this recommendation, assuming that the other agents also follow this recommendation, his expected payoff is going to be this number, right? Okay? So far? So good? But he can, rather than following the recommendation, he can deviate from the recommendation. So with probability mu hat S, this information is given. So I go to player 1 and I say, you should play S1. I go to player 2 and tell you should play S2. I go to player 3, you should play S3. But player 1 does not know what I told player 2 and 3. Player 2 and 2 does not know what I told player 1 and 3, and so on. Okay? So player I can play something else. Okay? So what should I put in here? Si prime. Don't write yet. And then we sum over. We sum over. Okay? We sum over what? Again, what are we trying to do? We're trying to find the expected payoff of player I if rather than following recommendation does something else. Sorry?
I mean, we're saying we sum the summation over the strategy profiles. It's a probability times the expected payoff of, but
It's the probability times the Bernoulli payoff, not the expected. Yeah.
the thing in brackets Si prime S minus I is another strategy profile.
Yes, exactly. Well, let's work with an example. Again, battle of sexes. Soccer opera, 2, 1, 1, 2, 0, 0, 0, 0. So now what I have to do is I have to specify a probability distribution over set of strategy profiles. So with what probability SS will be selected, with what probability SO will be selected, OS will be selected, OO will be selected. So rather than writing them separately, I'm going to write them inside. So consider, for example, 1 over 2, 0, 0, 1 over 2. So that's mu hat of SS is equal to 1 over 2. Mu hat of SO is equal to 0, and so on. That's what these numbers represent. Okay? So far, so good? Okay. So let me write this side before we formalize the definition. So what essentially you do is you tell your friend to call you and your wife or your spouse and report S to player 1 and S to player 2 with probability 1 over 2, and report or recommend O to player 1 and O to player 2 with probability 1 over 2. Okay? So the players can follow the recommendation, in which case the expected payoff is going to be 1 over 2 times 2 plus, well, this outcome will be realized with probability 0. 0 times 0 plus. This outcome will be realized with probability 0. 0 times 0 plus. This outcome will be realized with probability 1 over 2 times 1, which gives us 3 over 2. Okay? So this is what happens when player 1 is told to play S, and he follows the recommendation. And when he's told to play O, he follows the recommendation, without knowing what player 2 is told. But again, if I know this probability distribution, right? Here, why did I put a 0? Well, because if I know this probability distribution, when I'm told S, I know that my spouse is also told S. Okay? Because we both, me and my spouse, knows the probability distribution. We agree on mu hat. Okay? Now, if I deviate, what would happen? Yep.
I have a question for the
Here.
in mu of S times should be S prime.
So you think it should be S prime. Well, let's look at the story. So what is the thing happening? So me and my spouse, we agreed on this probability distribution. We asked one of our friends, our chairman, Refet Hoca, to toss a coin. And if it comes head, he's going to call both of us. And, well, he's going to call me first and then say, go to the soccer match. And then he's going to call my wife and say, go to the soccer match. If he tosses the coin and it comes up, what did I say, if tails or heads? Now, if it comes tails, he's going to call me and say, go to the opera. He's going to call my wife and say, go to the opera. Okay? But this he does irrespective of knowing what action I'm going to take. Okay? He tosses the coin, looks at the outcome, and calls me. And my action is realized after that. That's why this is S, not S prime. Okay? This is what this outside agent chooses, recommends to us. Okay? And he does that independent of our action. So what we do is, given that information, we can follow the recommendation or we can deviate from it. Okay? That's why this is S. What probability distribution?
Deviate. For example, with probability 1 over 2, I should follow S when the other player plays S. But if I deviate,
But I don't know. You see, when the other player plays S, I don't know what the other player is playing. But I'm assuming that it's fixed. That is, I'm assuming that the other player follows the recommendation.
if I deviate, I'll play O when the other player plays S. That he plays S. But with probability 1 over 2, so we'll have another probability distribution over S.
Look.
Like mu prime.
I don't have any coins. I usually carried a coin when I was teaching statistics. I haven't been teaching statistics anymore, so we do have a coin. Okay, so your two friends, one of you likes soccer, the other one likes opera better. So you're in the problem of coordinating. You asked me to do it. Okay, so I flipped a coin. Look at it, and it's a head. And then, without your friend knowing it, I say, go to the soccer match. And I go to your friend, and without you hearing it, I say, go to the soccer match. So, what can you do? Follow your instruction or deviate. But, you see, when you did the deviation decision, I have already flipped a coin. I have already made the recommendation. So how can the probability of saying soccer, soccer change? It's gone.
But if I deviate, it will be 0. The probability of soccer happening.
No, the probability that, you see, this is not the probability of the outcome realizing. It's the probability that I tell you to go to the soccer match, okay? Actually, maybe a different interpretation. We can do it, we can write it in a different way. So you see there's many ways to do something. Sometimes one is more illustrative than the other one. So let me change this definition once more. But before that, when you look at this, we haven't finished this definition. Does everything look good except that we don't agree on this? Again, you know, when you write these things, do accounting, okay? Ask, is everything accounted for? So we have an S. Is it accounted for? Yes. We have SI. Is it accounted for? Yes, it comes from here. S minus I. Is it accounted for? Yes. It's the component of this strategy profile. So here, everything is accounted for. Here, S, yes. S minus I, yes. SI prime? No. So there's a problem here we have to fix, okay? But let's leave that aside. Let me change the story. Actually, to make the story more interesting, let me change the probabilities here too. Otherwise it becomes, you see, the thing is, sometimes when things get too trivial, you get lost, okay? That's what I tried to do last lecture. I chose the mathematically simpler format, and I think it didn't work out. But this one, it was mathematically more complicated, and I hope it was more understandable, okay? So let's change these. Give me some probability distribution over here. Well, let's make it more interesting. Let's, for example, 1 over 3. Okay. So that's 0. Okay. Still, better than all equal, slightly, so I want to have some difference. Okay. Now, I call you and then say S to U. Okay. And that's all you hear. So I recommend that you play S. Calculate your expected payoff. Given this information, calculate the expected payoff. So I tossed, well, I didn't toss. I have a bag with 3 marbles, white, black, yellow, okay? If I choose the black marble, I'm going to say S to both. If I choose the white, I'm going to say S to player 1, O to player 2. If I pick the yellow one, I'm going to say O to player 1, S to player 2. Okay. So you're player 1. You're player 1. Okay. I pick the marble, and then, well, I don't tell you what color I saw. And I come to you and say, play S. What is your expected payoff? Try to write it first. We don't have too much time, but did I give the attendance sheet? Did everybody sign? Okay. No rush, we'll take it. What is given agent 1, given that is recommended to play S, that's S soccer. What is his expected payoff from following the recommendation? Yes. Did anybody find it? 2 over. I'm not good with numbers. I don't really. And this is, again, something that I learned from one of my supervisors, William Thompson. Whenever I told him that the answer was 2 over 3, He wouldn't like the answer. The reason is, where did 2 over 3 come from? It's not clear, okay? So it's better to say,
2 times 1 over 3
okay, 1 over 3 times 2.
plus 0 times
1 over
3 times
times 0. Same? Your friend has a different idea? Well, wait a minute. 1 over 2 times plus
1 over 2 comes from 1 over 3 divided by 1 over 2 plus.
So actually, it's not 1 over 2. That's 1 over 3 divided by
1 over 3 plus 1 over 3.
You see what your friend's doing? What is he doing? Conditional, Bayesian updating. Okay? So if player 1 is told to play S, then what would I, if I'm player 1, what would I think? Well, with equal likelihood, player 2, given this information, I would believe that player 2 will play S and O with equal probability, given that player 2 follows the recommendation. That is, with equal probabilities, player 2 would be recommended to play S and would be recommended to play O. Okay? So far, so good? So far, so good? Yes, sir. Bayesian, so it's so if A and B are 2 events, that is subsets of the set of possible outcomes of a random experiment, and if probability of B is different than 0, then the probability of A, given that we've informed that B has occurred, is equal to probability of A intersection B divided by probability of B. Okay? So updating, why? Before I was given any information, I thought that the probability of A, that is the likelihood of A occurring, was PA. Once I'm told that B has occurred, now I believe that the probability of A occurring is this number. So before I was told anything, the probability that I was assigning to SS, we agreed on a random device. The device was, there's 3 marbles in a bag. One of them is chosen. If it's black, SS will be reported, and so on. Okay? So given that both I and know this random device, we have probability of SS. So let me write it like this. Okay. But once I'm told that S has occurred, okay, then what happens? Probability of SS, given that I'm told that S has occurred, that is, given that so I'm sorry, not S has occurred, given that I'm recommended to play S, given that my component is S, is equal to what? Probability of this intersection, that is just SS. That's where 1 over 3 comes from. Okay? Divided by the probability of this event, which is 1 over 3 plus 1 over 3. Okay? Okay, so far so good? Any questions? Any questions? Okay, so this is when I'm told to play S, if I follow the recommendation, this is my expected payoff, which turned out to be equal to 1. Let me just finish this fast. What can I do? I can disregard the recommendation and play something else. Well, what else can I play? I only have one other option. If I play that option, what is my payoff? Sorry? So why 1 over 2? Why 1?
Because the probability of O happening is given the
The probability of O happening is?
I think it's 1 over 2 because the other player doesn't know that you're going to.
Again, so I'll say this and then finish, and then we'll go over this fast. Okay? The random device, the meditator, the third person, chose this ball and told you that the first component is S, told you that you should play S. Okay? That's a fact. That's something that has realized independent of your action. Okay? So, because that is the case, player 2 was told to play S. Given that you're told to play S, player 2 would be told to play S with probability 1 over 2. And player 2 would be told to play O with probability 1 over 2. Given that, you're told to play S. So your expected payoff is going to be, if you play O, 0 times 1 over 2 plus 1 times 1 over 2, which is less than 1. Well, we'll go over this again, but that will give you some chance to think about Bayesian updating, think about conditional probabilities, and this thing, okay? That's it. Have fun.